The radar operator at Murmansk Central Command Center stared at his screen and watched the impossible thing accelerate. His tracking system showed the aircraft crossing the Norwegian Sea at 85,000 feet and climbing, while his instruments registered a speed increase from Mach 2.8 to Mach 3.2 in less than 30 seconds. He had already transmitted the alert to Fighter Command 22 minutes earlier. Now he watched his SA-5 missile battery commander launch 2 Gammon missiles with maximum ceiling ratings of 98,000 feet, and he knew with absolute certainty they would fail before they even left their rails. The American reconnaissance aircraft was already 40 nautical miles beyond the intercept point his firing solution had calculated, and it was still accelerating. Every Soviet air defense operator along the northern perimeter had seen this same scenario unfold dozens of times, and every one of them had filed reports describing the same outcome. The target simply flew away from everything they launched at it. This was August 15, 1986, and Soviet air defenses had been trying to stop this aircraft for 20 years. Major Mikhail Mayaky was already climbing through 52,000 feet in his MiG-31 Foxhound, when the ground controller confirmed the target altitude at 87,000 feet and Mach 3.3. His R-33 missiles were designed specifically to kill this target. The Americans called it the SR-71 Blackbird, and it had been photographing Soviet military installations with complete impunity since January of 1966. Mayaky achieved radar lock at 120 kilometers exactly as his training prescribed, and his fire control system showed a theoretical intercept solution. But the SR-71 was flying in international airspace exactly 12 nautical miles beyond Soviet territorial waters, and his orders were explicit: observe, track, and demonstrate capability, but do not fire unless the target violates the border. He watched his altitude indicator climb to 65,676 feet, the absolute maximum performance ceiling of his aircraft with a full weapons load, while the American aircraft maintained steady altitude 7 miles above him and pulled steadily away at a speed his MiG-31 could not sustain for more than a few minutes without destroying its engines. The Americans had been flying these missions along the Soviet border for 2 decades, and Soviet Air Defense Command had fired more than 4,000 missiles at the aircraft without recording a single kill. The SA-2 guideline missiles that had destroyed Francis Gary Powers' U-2 reconnaissance aircraft over Sverdlovsk on May 1, 1960, could accelerate to Mach 3.5, but they were designed to intercept targets at 60,000 feet traveling at subsonic speeds. The SR-71 cruised at 85,000 feet at Mach 3.2, and by the time the SA-2's booster stage burned out and the liquid fuel sustainer ignited, the Blackbird was already 6 miles beyond the missile's kinematic intercept envelope. Soviet radar operators had learned to recognize the characteristic pattern. The target would appear on their screens traveling at speeds their manuals said were impossible for sustained flight. Their SA-2 batteries would launch, and the Americans would simply continue on their programmed route as if nothing had happened. Some missiles came within 150 yards of their targets. Most fell short by several miles. None had ever damaged the aircraft they were meant to destroy. The psychological impact on Soviet air defense personnel was profound and carefully documented in classified reports that wouldn't surface for decades. Major Mayaky later described the moment the alert sounded at his base. The alarm with shrill bell, confirmed by loudspeaker. To this day I have been averse to school bells because a bell was the first signal for a burst of adrenaline. The appearance of an SR-71 was always accompanied by nervousness. Everyone began to talk in frenzied voices, to scurry about, react with excessive emotion. He explained that the speed and altitude of the American aircraft simply hypnotized everyone at his base, and each attempted intercept was treated as top priority, not just for fighter aviation but for the entire 10th Army of the Soviet PVO air defense forces. These were not inexperienced operators responding to an unknown threat. These were elite units trained specifically to counter high-altitude reconnaissance aircraft, equipped with the most advanced interceptors and missiles Soviet industry could produce, and they understood with increasing clarity that they were facing a performance envelope they could not reach. What Soviet Air Defense Command didn't know, couldn't know, and wouldn't fully understand until after the Cold War ended, was that the SR-71's performance margins were even greater than what they observed. The aircraft they tracked at Mach 3.2 was capable of sustained cruise at Mach 3.3, emergency dash speeds above Mach 3.5, and classified performance characteristics that remained secret decades after the last operational flight. American pilots had standing orders to accelerate when missiles were detected, and the additional speed margin was usually sufficient to simply outrun the incoming weapons. The Soviets were observing the Blackbird's standard operational performance, not its maximum capability, and even that standard performance exceeded every intercept solution their most advanced systems could calculate. They were fighting an engagement where the fundamental physics favored their opponent so completely that tactical excellence became irrelevant. The story of how America built an aircraft that could fly with impunity through the most heavily defended airspace in history began on May 1, 1960. When France's Gary Powers U-2 reconnaissance aircraft was shot down over the Soviet Union at 66,000 feet. President Dwight Eisenhower had authorized the overflight personally, believing CIA assurances that the U-2 flew too high for Soviet missiles to reach. Powers survived his aircraft's destruction, and his subsequent interrogation proved the CIA assessment catastrophically wrong. The Soviets had tracked every U-2 flight over their territory and had been refining their SA-2 guideline missile tactics specifically to engage these high-altitude reconnaissance missions. Powers' shootdown wasn't a lucky hit. It was the successful execution of a systematic Soviet counter-reconnaissance program that had been tracking American intelligence-gathering flights for more than 3 years. The U-2 crisis triggered immediate policy changes and long-term strategic reassessments across American intelligence agencies. Eisenhower banned all manned reconnaissance over flights of Soviet territory, a prohibition that would remain in effect through multiple administrations. The Central Intelligence Agency requested an aircraft with higher ceiling and substantially greater speed than the U-2, and they turned to the only organization they believed capable of delivering such a platform: Lockheed's Advanced Development Projects Division at Burbank, California, better known as the Skunk Works. The division's leader was Clarence Leonard Kelly Johnson, a 50-year-old aircraft designer who had already created the P-38 Lightning fighter, the P-80 Shooting Starjet, and the U-2 itself. Johnson had built the Skunk Works on principles that contradicted every standard aerospace industry practice: small teams, minimal paperwork, maximum authority for the project leader, and absolute insulation from corporate bureaucracy. The CIA's requirements seemed impossible, even by Skunk Works standards. They needed an aircraft capable of sustained cruise above 80,000 feet at speeds exceeding Mach 3, with transcontinental range and payload capacity for advanced reconnaissance sensors. The platform would need to resist radar detection, survive temperatures that would melt conventional aircraft structures, and operate reliably despite thermal expansion that would open gaps in its fuel tanks during ground operations. It would need to take off and land on conventional runways, despite flying at speeds where aerodynamic heating would turn its titanium skin cherry red. Most critically, it would need to fly so high and so fast that Soviet missiles and fighters couldn't reach it. Because American policy now prohibited the kind of calculated risk-taking that had led to Powers' capture, Johnson approached the project with a philosophy he articulated to his team at the first design meeting: start from scratch as if we are building the first airplane, just like the Wright brothers. He assembled a team of 134 engineers and gave them a directive that defined Skunk Works culture: be quick, be quiet, and be on time. He limited written reports to 20 pages maximum because he didn't have time to read lengthy documents. He restricted meetings to 15 people or fewer. He gave individual engineers authority to make decisions that would require executive board approval at conventional aerospace companies. He created an environment where technical excellence and speed of execution mattered more than organizational hierarchy or bureaucratic process. The team he assembled would design and build the most sophisticated aircraft in history in less time than conventional programs required to complete preliminary design reviews. The technical challenges were unprecedented and interconnected in ways that made conventional engineering approaches inadequate. The aircraft would need to fly at speeds where air friction heated its skin to 1100 degrees Fahrenheit, temperatures that would cause aluminum to weaken and eventually melt. Titanium was the only practical structural material, but titanium presented its own cascade of problems. The metal was expensive, difficult to machine, and extremely sensitive to contamination. Conventional cutting tools failed when used on titanium because they introduced corrosion. Cadmium-plated tools caused titanium to become brittle. Even the water used to cool cutting equipment mattered because chlorine in municipal water supplies corroded titanium at elevated temperatures. The Skunk Works team had to develop entirely new tooling, manufacturing processes, and quality control procedures for a material that American aerospace industry had minimal experience working with. The titanium supply chain created a separate set of problems with Cold War implications. The United States produced limited quantities of titanium in 1960, and most domestic production was already committed to other defense programs. The Soviet Union was the world's largest titanium producer, but direct purchases from Soviet sources were impossible for a classified American reconnaissance program. The CIA created a network of shell corporations that purchased titanium on the world market, much of it ultimately originating from Soviet mills, which Soviet metallurgists then processed into aircraft components that would be used to spy on their own military installations. The Soviets were unknowingly supplying the raw materials for their own surveillance. Kelly Johnson's team spent 18 months developing the A-12, a single-seat reconnaissance aircraft that would serve as the direct predecessor to the SR-71. The A-12's design incorporated radical innovations that would define high-speed flight for decades. The fuselage was blended with the wing to create a continuous lifting surface, reducing drag and improving fuel efficiency. The engine inlets were positioned well back from the nose to allow the shock wave from supersonic flight to stabilize before entering the engines. The fuel tanks were integral to the airframe structure, with the aircraft's outer skin serving as tank walls. This design created a persistent problem. The panels would fit loosely when the aircraft was cold on the ground, allowing fuel to leak from gaps that wouldn't seal until thermal expansion closed them during high-speed flight. Maintenance crews at operational bases would position drip pans under parked Blackbirds to catch JP-7 fuel leaking from dozens of panel joints, and pilots learned to expect fuel puddles beneath their aircraft during pre-flight inspections. The aircraft's propulsion system required innovations as radical as the airframe. Pratt & Whitney designed the J-58 engine specifically for sustained Mach 3 cruise, and the engine operated on principles that blurred the distinction between turbojet and ramjet. At speeds below Mach 2, the J-58 functioned as a conventional afterburning turbojet, with all thrust generated by the engine's turbine and combustion chamber. Above Mach 2, a series of bypass tubes opened to allow some incoming air to flow around the engine core and mix with exhaust gases in the afterburner section. At Mach 3 cruise, 54% of the aircraft's thrust came from the inlet shockwave management system, 17.6% came from the engine itself, and 28.4% came from the ejector nozzle that managed exhaust flow. The J-58 was effectively a variable cycle engine that transitioned from turbojet to turbo-ramjet to ramjet-dominated propulsion as speed increased, and it was the only engine in operational service capable of producing 32,500 pounds of thrust while running continuously in full afterburner. Ben Rich, who would later succeed Kelly Johnson as head of the Skunk Works, called the inlet control system the most exhausting, difficult, nerve-wracking work of the entire program. The inlet had to slow supersonic air to subsonic speeds before it entered the engine, manage the shock wave patterns that formed at different Mach numbers, and maintain stable airflow despite constant variations in altitude and speed. A failure in the inlet control system produced a condition pilots called an unstart, where the shock wave pattern would suddenly shift and normal airflow would collapse. An unstart created violent yaw that could throw the aircraft off course by 30 degrees in less than a second. Pilots had to manually adjust inlet spike positions to restore normal airflow while compensating for asymmetric thrust and maintaining altitude and heading. The process required immediate recognition, precise control inputs, and absolute confidence in extremely hostile flight conditions. The A-12 first flew on April 24, 1962, when test pilot Lou Schalk accidentally became airborne during high-speed taxi tests at Groom Lake, Nevada. The aircraft demonstrated performance that exceeded CIA requirements and validated Johnson's design approaches. Maximum speed exceeded Mach 3.2. Service ceiling reached 88,000 feet. Range with a single aerial refueling exceeded 3,000 miles. The aircraft was nearly invisible to contemporary radar systems because its shape produced minimal radar returns, and its skin was coated with iron ferrite paint that absorbed radar energy. Test flights revealed handling characteristics that were surprisingly benign at cruise conditions, with pilots reporting the aircraft was stable and responsive despite flying at speeds where control inputs took several miles to produce visible course changes. President Lyndon Johnson publicly announced the existence of the Blackbird program on February 29, 1964, revealing that the United States had developed an advanced reconnaissance aircraft capable of speeds above 2,000 miles per hour and altitudes above 70,000 feet. The announcement was deliberately vague about specific performance characteristics, and the aircraft Johnson described was designated the A-11, a designation that didn't actually exist but provided plausible cover for the classified A-12 program. On July 24, 1964, Johnson announced the SR-71 variant specifically, describing it as an interceptor and strategic reconnaissance platform that would enter service with the United States Air Force. The public announcements served multiple purposes. They demonstrated American technological superiority, they provided political benefits during an election year, and they allowed the program to transition from purely classified development to operational deployment with appropriate public awareness. The SR-71 differed from the A-12 in several important respects. The airframe was slightly longer to accommodate a second crew member, a reconnaissance systems officer, who operated the aircraft's sensor package from a separate cockpit behind the pilot. The sensor bay was enlarged to carry a wider range of reconnaissance equipment, including optical cameras, infrared sensors, side-looking airborne radar, and signals intelligence collection systems. The aircraft's range was extended through increased fuel capacity. The production version incorporated lessons learned from A-12 test flights, including improved inlet controls, refined aerodynamics, and better thermal management systems. The changes added weight and slightly reduced maximum speed, but they created a more capable reconnaissance platform that could gather multiple intelligence types on a single mission. The first production, SR-71, tail number 61 MISR 7950, was delivered to Air Force Plant 42 at Palmdale, California on October 29, 1964. Lockheed test pilot Bob Gilland flew the first SR-71 flight on December 22, 1964, validating the aircraft's systems and performance. The Air Force announced that Beale Air Force Base in California would serve as the SR-71's home base on December 7, 1964, and the first operational aircraft was delivered to the 4,200th Strategic Reconnaissance Wing at Beale in January of 1966. The unit was later redesignated the 9th Strategic Reconnaissance Wing, and it would remain the only SR-71 wing throughout the aircraft's operational life. Lockheed built 32 SR-71 aircraft in total, 29 SR-71A operational reconnaissance variants, 2 SR-71B trainers with raised rear cockpits for instructor visibility, and 1 SR-71C hybrid testbed built from an SR-71 forward fuselage and a YF-12 rear fuselage. On February 5, 1968, with production complete, Lockheed received orders to destroy all A-12, YF-12, and SR-71 tooling and manufacturing equipment. The destruction order was intended to prevent unauthorized production and ensure that sensitive manufacturing techniques remained secure, but it also meant that the SR-71 fleet could never be expanded beyond the 32 aircraft already built. Any aircraft lost to accidents or combat would reduce total fleet strength permanently. The SR-71 entered operational service during the height of American involvement in Vietnam, and the first combat deployment came on March 8, 1968, when SR-71s arrived at Kadena Air Base in Okinawa, Japan. The unit was designated Operating Location OL-8, later redesignated Detachment 1. Major Jerome O'Malley and Major Edward Payne flew the first operational SR-71 sortie on March 21, 1968. Photographing targets in North Vietnam from altitudes the North Vietnamese air defense system couldn't reach. The CIA had flown A-12 missions over Vietnam starting in May of 1967, but the SR-71 brought greater payload capacity and longer loiter time over target areas. North Vietnamese air defenses had been refined through years of combat against American tactical aircraft, and the system was built around thousands of Soviet-supplied SA-2 guideline missiles. The SA-2 had proven effective against high-altitude targets, destroying Gary Power's U-2 in 1960 and Major Rudolph Anderson's U-2 over Cuba during the missile crisis in October of 1962. North Vietnamese missile operators were experienced, well-trained, and supported by an extensive radar network that could track incoming aircraft and direct multiple missile batteries against coordinated targets. American tactical aircraft losses to SA-2 missiles were substantial, and mission planners developed elaborate tactics to suppress or avoid surface-to-air missile threats. The SR-71 required no such tactics. It simply flew too high and too fast for the SA-2 system to engage effectively. North Vietnamese missile operators launched approximately 800 SA-2 missiles at SR-71 aircraft during the war. None achieved a kill, and most fell several miles short of their intended targets. The SA-2's two-stage design used a solid fuel booster that burned for 4 to 5 seconds to accelerate the missile off its launcher. followed by a liquid fuel sustainer that burned for 22 seconds to propel the missile to intercept altitude. Maximum missile speed was Mach 3.5, slightly faster than the SR-71's cruise speed, but the missile had to climb from ground level to 85,000 feet, while the SR-71 was already at cruise altitude and moving away from the launch point at over 2,000 miles per hour. The missile's kinematic performance was theoretically sufficient to reach the SR-71's altitude, but only if the target aircraft maintained constant altitude and heading, and the intercept geometry was nearly perfect. SR-71 pilots reported that North Vietnamese missiles were sometimes launched without radar guidance, suggesting that operators were firing on predicted flight paths rather than active tracking data. Several pilots reported missiles passing within 150 yards of their aircraft, close enough to see the weapons visually but not close enough for proximity fuses to detonate. The closest approaches usually occurred when the SR-71 was flying a predictable route at constant altitude, giving missile operators their best opportunity to calculate an intercept point. American doctrine called for immediate acceleration and altitude changes when missile launches were detected, and the additional speed margin was usually sufficient to move the aircraft outside the missile's intercept envelope before the weapon reached maximum altitude. One A-12 aircraft returned to base after a mission over North Vietnam with physical evidence of an SA-2 engagement that came closer than any crew realized during flight. Post-flight inspection at altitude above 82,000 feet revealed debris embedded in the composite inboard leading edge. CIA analysts identified the debris as a fragment from an SA-2 fusing mechanism. The missile had apparently detonated close enough for fragments to reach the aircraft, but the warhead blast was insufficient to cause significant damage at the distance where detonation occurred. The incident proved that North Vietnamese missiles could reach the A-12's operating altitude under optimal conditions, but it also demonstrated that even a near miss was insufficient to bring down the aircraft. The A-12 survived an engagement that would have destroyed any conventional reconnaissance platform and returned to base with damage so minor that flight crews didn't notice it until ground inspection. The SR-71's invulnerability had profound implications for intelligence gathering throughout the Vietnam War. While tactical reconnaissance aircraft had to navigate heavily defended airspace at medium altitudes where they were vulnerable to missiles and anti-aircraft artillery, the SR-71 flew routes that were planned without regard to ground threats. The aircraft could photograph 100,000 square miles per hour from cruise altitude, with camera resolution sufficient to identify vehicle types and read large text from 85,000 feet. It could map electronic emissions across entire regions, cataloging radar installations and communications networks in a single pass. It could provide pre-strike reconnaissance for tactical bombing missions and post-strike battle damage assessment without risking crew or aircraft. The intelligence advantage was so substantial that mission planners scheduled SR-71 flights whenever time-sensitive targeting information was required, confident that the aircraft would return with the requested imagery. Soviet Air Defense Command watched American SR-71 operations over Vietnam with close attention and growing concern. They were supplying the SA-2 missiles that North Vietnamese forces fired at the Blackbird, and they received detailed reports on every engagement. The pattern was consistent and deeply troubling. American reconnaissance aircraft were operating with complete impunity at speeds and altitudes Soviet missiles couldn't reach. The implications extended far beyond Southeast Asia. If American reconnaissance aircraft could fly freely over North Vietnam despite the presence of thousands of Soviet missiles and hundreds of trained operators, what would happen if similar aircraft flew along Soviet borders or potentially over Soviet territory? The question drove urgent efforts to develop new missiles and fighter aircraft capable of engaging high-altitude, high-speed targets. The MiG-25 Foxbat was Soviet aviation industry's answer to the high-speed reconnaissance threat. Development had begun in the early 1960s in response to American programs like the B-70 Valkyrie bomber, and the aircraft entered service in 1964. The MiG-25 could reach speeds above Mach 3 and altitudes above 78,000 feet, performance that exceeded any other operational fighter in the world. Soviet planners believed the MiG-25 would be capable of intercepting the SR-71, and they began deploying the aircraft to bases where it could respond to American reconnaissance missions. The deployments were accompanied by revised tactical doctrine that emphasized coordinated intercepts, optimal geometry for missile shots, and maximum performance profiles designed to bring MiG-25 interceptors within firing range of their targets. The reality proved disappointing. The MiG-25's maximum speed of Mach 3.2 could only be sustained for brief periods before the engines began to overheat and damage themselves. The aircraft's service ceiling with a combat load of 4 R-40 missiles was 68,900 feet, substantially lower than the SR-71's standard cruise altitude. With only 2 missiles, the MiG-25 could reach 78,000 feet, but even this maximum altitude left the fighter several miles below its target. The R-40 missiles were large, long-range weapons designed for intercepts against bomber formations, but they lacked the velocity to overtake a Mach 3 target in a tail chase, and their guidance systems couldn't track targets with the low radar cross-section that the SR-71 presented. Soviet pilots quickly learned that MiG-25 intercepts of SR-71 aircraft were exercises in futility, with the American aircraft maintaining comfortable altitude and speed margins that made weapons employment impossible. Lieutenant Viktor Belenko provided definitive confirmation of Soviet assessment when he defected to Japan in his MiG-25 on September 6, 1976. Belenko's debriefing by American intelligence officers included extensive discussion of Soviet air defense capabilities and tactics against high-performance reconnaissance aircraft. His testimony was unambiguous. First of all, the SR-71 flies too high and too fast. The MiG-25 cannot reach it or catch it. Secondly, the missiles are useless above 27,000 meters, and the SR-71 cruises much higher. Even if we could reach it, our missiles lack velocity to overtake the SR-71 in a tail chase. In a head-on attack, our guidance systems cannot adjust to the high closing speed. Belenko explained that shooting down an SR-71 was the holy grail of Soviet air defense, the one achievement that would guarantee recognition and advancement for any pilot or unit that accomplished it. The fact that no one had succeeded despite years of attempts was proof of how completely the task exceeded Soviet capabilities. Belenko's information confirmed what American intelligence had suspected but couldn't verify through technical means alone. The SR-71's performance margins were sufficient to defeat the Soviet Union's most advanced interceptor under all operationally relevant conditions. The MiG-25 couldn't reach the Blackbird's cruise altitude with sufficient speed to employ weapons effectively, and even if optimal intercept geometry could be achieved, Soviet missiles lacked the kinematic performance to complete the engagement. The psychological impact on Soviet pilots was significant, with frustration evident in the frenzied activity that accompanied each alert, the knowledge that their best efforts would be insufficient, and the standing orders to attempt intercepts despite the near certainty of failure. Soviet pilots along the Baltic Sea border developed tactics that theoretically improved their chances against SR-71 flights from RAF Mildenhall in the United Kingdom. Detachment 4 began operations at Mildenhall on April 20, 1976, flying reconnaissance missions along the Soviet border that NATO designated Baltic Express. The missions followed a precise route through the narrow international airspace between Scandinavia and Eastern Europe, overflying international waters while Soviet radar operators tracked every mile. MiG-25 interceptors from Finno-Eberswalde in East Germany would climb to their maximum altitude of 62,000 feet and positioned themselves approximately 1.9 miles behind SR-71 aircraft cruising at 72,000 feet. The closure was as close as Soviet fighters could achieve, and Swedish intelligence interpreted these intercepts as simulated shootdowns that demonstrated Soviet capability to engage the Blackbird under ideal conditions. The Soviet interpretation was different. MiG-25 pilots understood they were demonstrating maximum effort capability, not combat effectiveness. They could position themselves in trail behind the SR-71, but they couldn't close the altitude gap or maintain position long enough to employ weapons. They could achieve radar lock momentarily before the target aircraft pulled away, but their missiles couldn't reach a target that was simultaneously several miles higher and traveling 200 miles per hour faster than their maximum sustained speed. The intercepts were valuable for training purposes, and they provided psychological benefit by demonstrating that Soviet forces were actively contesting American reconnaissance missions, but they didn't change the fundamental reality that the SR-71 could fly wherever it wanted along the Soviet border with complete impunity. Swedish Air Force, JANA 37 Viggen fighters, introduced a different tactical approach during Baltic Express missions. The Viggen's maximum speed of Mach 2.1 and service ceiling of 59,000 feet were insufficient for tail chase intercepts. But Swedish pilots developed frontal attack profiles that took advantage of the aircraft's sophisticated avionics. A Vigan pilot would position his aircraft in front of the SR-71's known flight path, usually between the Swedish islands of Öland and Gotland, and wait for the American aircraft to approach. The combined closing speed approached Mach 5, and the Vigan's radar system could achieve lock-on briefly as the SR-71 passed. Swedish Air Force records claim 51 successful missile locks out of 322 documented Baltic Express sorties, a success rate of 15.8%. The tactic required the SR-71 to fly a predictable route at constant altitude, and it demonstrated what could theoretically be achieved with optimal positioning and modern avionics. But no Swedish pilot ever fired a live missile at an SR-71, and the effectiveness of an actual engagement remained theoretical. Soviet Air Defense Command understood that intercepting the SR-71 with existing systems was effectively impossible, and they initiated programs to develop new weapons specifically designed to counter the high-altitude reconnaissance threat. The MiG-31 Foxhound entered service in the early 1980s with substantial improvements over the MiG-25. The aircraft was faster, flew higher, carried more capable missiles, and featured advanced radar that could track multiple targets simultaneously. The R-33 missile was roughly comparable to the American AN-54 Phoenix, with long-range, high-speed and sophisticated guidance that made it effective against targets with low radar cross-sections. Soviet planners believed the MiG-31 would finally give them the capability to threaten American reconnaissance aircraft, and they deployed the type to bases where it could respond to SR-71 missions along the Soviet border. Major Mikhail Myak flew MiG-31 intercepts against SR-71 aircraft throughout the 1980s, and his accounts provide detailed insight into Soviet tactics and assessment of their own capabilities. An alert for an SR-71 intercept would sound approximately 11 minutes after American intelligence detected activity suggesting mission preparation at Mildenhall. Ground controllers would vector the MiG-31 to an intercept point based on predicted SR-71 flight path, and the pilot would climb to maximum altitude while accelerating to supersonic speed. Myak achieved radar lock on an SR-71 on January 31, 1986, at a distance of 120 kilometers while climbing through 52,000 feet. He continued climbing to 65,676 feet, his maximum altitude with full weapons load, while maintaining lock on the American aircraft cruising at 87,000 feet, approximately 7 miles above him. Myak's assessment was more optimistic than earlier Soviet evaluations, but it included critical limitations. He stated that if the SR-71 violated Soviet airspace, there was practically no chance the aircraft could avoid an R-33 missile, assuming the MiG-31 pilot had adequate warning and could position for intercept before the target crossed the border. The statement revealed both the MiG-31's capability and its operational constraints. The aircraft could theoretically engage the SR-71 if the American aircraft entered Soviet airspace and maintained a predictable flight path long enough for missile intercept to occur. But American reconnaissance policy since 1960 had prohibited overflights of Soviet territory, and SR-71 pilots maintained strict discipline in respecting the 12 nautical mile territorial limit. The aircraft that Myak tracked on radar was always outside Soviet airspace, and it would remain outside Soviet airspace for the entire mission, making his theoretical intercept capability operationally irrelevant. Lieutenant Colonel Ed Yielding experienced the Soviet perspective from the opposite side during a Baltic Express mission between August 25 and October 8, 1986. Yielding and his reconnaissance systems officer Kurt Osterheld were conducting their reconnaissance run along the standard route when radar warning receivers indicated MiG-31 radar lock. The indication wasn't unusual. Soviet interceptors had been attempting locks on Blackbird missions for years. What was unusual was the quality of the lock and the duration for which it was maintained. Yielding recognized that Soviet capabilities had improved substantially, and he understood that the MiG-31 pilot likely had a valid firing solution. He also understood that his aircraft was operating in international airspace exactly where his flight plan indicated it would be, and that his programmed turn away from Soviet territory would occur at the precise point required to maintain legal separation from Soviet territorial waters. Yielding later reflected on the psychological dimension of these encounters. He imagined the Soviet fighter pilot was much like himself, with a love of aviation and determination to excel at his profession. He assumed the Soviet pilot had orders to fire if the SR-71 was late with its turn and slipped over Soviet territorial waters within 12 nautical miles of Soviet land. The SR-71 would be a prize target for any Soviet pilot who achieved a kill. Yielding noted that American crews in the 1980s were not concerned about missiles as long as they maintained high altitude and high speed. They believed missile maneuverability, range and proximity fuses were not adequate to bring down a Mach 3 aircraft in the thin air above 80,000 feet. The SR-71's low radar reflectivity further decreased missile probability of kill, and the aircraft carried electronic countermeasures that provided additional protection. American confidence was based on 20 years of operational experience during which more than 4,000 missiles had been fired at Blackbirds without achieving a single kill. The operational reality was more nuanced than either American or Soviet assessments. Fully captured, the MiG-31's R-33 missile probably could intercept an SR-71 under specific circumstances. If the aircraft violated Soviet airspace, if it maintained a predictable flight path long enough for the missile to complete its intercept, if the engagement geometry was favorable, and if the missile performed at the upper end of its specification envelope. But American operational doctrine eliminated most of these conditions by keeping reconnaissance aircraft outside Soviet territory, by authorizing immediate evasive maneuvers when missile launches were detected, and by maintaining classified performance margins that exceeded the speed and altitude Soviet intelligence believed the SR-71 could achieve. The engagement was fundamentally asymmetric, with American aircraft operating from a sanctuary of international airspace and performance margins that made even sophisticated Soviet weapons marginally effective at best. June 3, 1986 marked a significant demonstration of improved Soviet capability when 6 MiG-31 aircraft conducted a coordinated intercept of an SR-71 over the Barents Sea. The intercept profile was sophisticated, with multiple aircraft positioned to achieve all-angle attack coverage that would theoretically allow missile shots, regardless of which direction the target aircraft maneuvered. Soviet Air Defense Command treated the mission as a high-priority training exercise and propaganda opportunity, demonstrating that they could mass sufficient forces to threaten even the most capable American reconnaissance platforms. Western intelligence analyzed the intercept carefully and concluded that Soviet capabilities had improved substantially since the MiG-25 era. American SR-71 operations reportedly began shifting toward standoff reconnaissance from positions outside Soviet borders, using long-range sensors to gather intelligence on coastal installations without entering airspace where MiG-31 intercepts could occur. The Chinese People's Liberation Army Air Force developed their own anti-SR-71 capability based on Soviet technology and Chinese industrial adaptations. The HQ-3 missile was a Chinese variant of the SA-2 guideline specifically redesigned to engage high-altitude, high-speed targets. Maximum ceiling was 30 kilometers, approximately 98,425 feet, with maximum range of 42 kilometers and speed of Mach 3.5. The Chinese built 150 HQ-3 missiles and deployed them to sites where they could threaten American reconnaissance aircraft approaching Chinese airspace. There is no documented case of an HQ-3 engaging an SR-71, but the missile's specifications suggest it would have faced the same limitations that plagued Soviet SA-2 batteries: insufficient speed to overtake the target in tail chase, marginal kinematic performance for intercept at maximum range, and guidance systems that struggled with low radar cross-section targets at extreme altitude. Operational tempo at Kadena Air Base in Okinawa reflected the SR-71's central role in American intelligence collection throughout Asia. Early in the program, the unit flew approximately one sortie per week per aircraft, with each mission requiring extensive pre-flight preparation and post-flight maintenance. By 1972, fleet-wide sortie rate had increased to nearly one mission per day, demonstrating improved maintenance procedures and greater confidence in aircraft reliability. The most active SR-71 in the fleet, tail number 61-7976, accumulated 2,981 flying hours over 942 total sorties, including 257 operational missions. The aircraft flew the first operational SR-71 sortie on March 21, 1968, and it remained in service until the program's termination in 1990, compiling a service record that demonstrated both the aircraft's durability and the intensity of its operational use. Technical sophistication of the SR-71's reconnaissance systems matched the performance of its airframe and propulsion. Optical cameras could photograph license plates on vehicles from cruise altitude, providing imagery intelligence with resolution that rivaled low-altitude tactical reconnaissance. Side-looking airborne radar could map terrain features and identify vehicle concentrations through clouds and at night, providing all-weather reconnaissance capability. Signals intelligence sensors could intercept and geolocate electronic emissions, mapping radar networks and communications systems across entire regions in a single pass. The combination of sensors meant that a single SR-71 sortie could collect photographic intelligence, electronic intelligence, and radar imagery simultaneously, providing a comprehensive intelligence picture that would otherwise require multiple missions by different aircraft. Electronic countermeasures evolved throughout the SR-71's service life as Soviet radar and missile systems improved. Early aircraft carried DEF defensive systems in several variants, DEF A, B, C, E, and G configurations that provided jamming and deception against contemporary Soviet radars. Later variants included improved DEF A2 and C2 systems with expanded frequency coverage and greater power output. Final variants included DEF H and M systems and eventually a programmable A2C system that could be reprogrammed to counter new threats as Soviet systems evolved. The continuous evolution of defensive systems reflected the ongoing competition between American reconnaissance capabilities and Soviet air defense improvements, with each side adapting to the other's innovations in a technological contest that lasted throughout the Cold War. Colonel Darrell Cobb experienced one of the few documented cases where Soviet missiles came close to hitting an SR-71 under operational conditions. Cobb was flying a reconnaissance mission in international waters near Vladivostok when a MiG-25 interceptor fired a missile at his aircraft. The SR-71 was maintaining standard altitude and speed approximately 12 nautical miles from Soviet territorial waters, exactly where international law permitted intelligence-gathering operations. The missile was visible to the crew during its approach, and the aircraft's radar warning receivers provided indication of the guidance system. Cobb maintained his planned flight path and speed, confident that the missile lacked sufficient performance to close the gap. The missile failed to connect, falling away as its kinetic energy exhausted before reaching intercept range. The engagement validated American confidence in the SR-71's performance margins and demonstrated that even when Soviet fighters achieved favorable positioning and weapons employment, their missiles couldn't overcome the fundamental physics that favored the faster, higher target. Loss rates for the SR-71 fleet were remarkably low despite the aircraft's operational intensity and technical complexity. 12 SR-71s were lost to accidents during the program's operational life, but 0 were lost to enemy action. The safety record was particularly notable given the extreme flight conditions, the sustained high-speed flight that subjected airframes to enormous thermal and structural stress, and the fact that many systems were operating at the edge of technical feasibility. The first SR-71 lost in 17 years occurred in 1989 when SR-71 tail number 974, nicknamed Ichban, experienced catastrophic engine failure and broke apart 0.25 miles north of Luzon in the Philippines on April 21. Pilot Dan House and reconnaissance systems officer Blair Bozek ejected successfully and reached shore safely. The accident investigation revealed mechanical failure rather than design flaw, and the remaining fleet continued operations with confidence in the aircraft's fundamental soundness. Program costs were substantial and increasingly difficult to justify as budget pressures intensified and alternative intelligence collection methods matured. Each SR-71 sortie required extensive preparation time, with minimum 19 hours required to prepare an aircraft for mission readiness. Post-flight maintenance often revealed missing rivets, delaminated panels, and damage to inlet structures from the extreme conditions of sustained Mach 3 cruise. Ground crews would find JP-7 fuel leaking from dozens of panel joints during pre-flight inspections, requiring drip pans positioned under parked aircraft to catch fuel until thermal expansion sealed the gaps during flight. Specialized parts were increasingly difficult to obtain as the tooling to manufacture titanium components had been destroyed in 1968. The aircraft required specialized maintenance personnel trained in techniques that had no application to other aircraft types, and maintaining that expertise became more challenging as personnel rotated to other assignments and institutional knowledge eroded. Space-based reconnaissance systems provided an alternative intelligence collection method that didn't require aircraft penetration of hostile airspace or acceptance of crew risk. Satellite imagery resolution improved throughout the 1970s and 80s, and by the late 1980s, satellites could provide imagery comparable to SR-71 optical cameras without the operational complexity of manned reconnaissance flights. Satellites had limitations. They followed predictable orbits that allowed adversaries to conceal activities when overhead passes were scheduled. They couldn't be quickly retasked to respond to emerging intelligence requirements, and they provided intermittent coverage rather than continuous surveillance. But satellites were cheaper to operate than SR-71 missions, they didn't risk crew lives, and they couldn't be shot down by improving Soviet air defense systems. The combination of high operating costs, improving Soviet capabilities, and maturing satellite reconnaissance created political pressure to terminate the SR-71 program, despite its unique capabilities. The Air Force and intelligence officials announced program termination in 1989, with final operational flights scheduled for early 1990. The last training flight occurred on November 7, 1989, with pilot Tom McCleary and reconnaissance systems officer Stan Gudmundsson at the controls, marking 21 years, 7 months, and 7 days of operational service since the first SR-71 flight. The last SR-71 departed Kadena Air Base on January 21, 1990, ending more than 2 decades of reconnaissance operations from Okinawa. Official decommissioning ceremonies at Beale Air Force Base took place on January 26, 1990, with military and civilian officials acknowledging the aircraft's contributions to national security while defending the decision to terminate the program. The final SR-71 flight captured public attention and demonstrated the aircraft's enduring performance even as it passed into history. Lieutenant Colonel Ed Yielding and Lieutenant Colonel Joseph Vida flew SR-71 tail number 61 NI 7972 from Los Angeles to Washington Dulles International Airport on March 6, 1990, covering the distance in 1 hour, 4 minutes and 20 seconds at an average speed of 2,124 miles per hour. The flight set multiple speed records and served as a final demonstration of capabilities that had defined American reconnaissance for nearly a quarter century. The aircraft was delivered to the Smithsonian National Air and Space Museum, where it would be preserved as an artifact of Cold War technological competition and American aerospace achievement. Congress briefly revived the program in 1995 over military objections, authorizing funding to return several SR-71 aircraft to operational status. The Air Force complied with congressional direction but made clear its preference for satellite reconnaissance and concern about the costs of maintaining a unique aircraft type with specialized support requirements. The revival lasted until 1997, when budget conflicts and lack of military enthusiasm led to final termination. NASA continued flying SR-71 aircraft for research purposes until October of 1999. When the last Blackbird flight occurred and the program ended permanently after more than 3 decades of service. The fundamental question of whether Soviet forces knew the SR-71 was invulnerable to their missiles has a complex answer that evolved throughout the aircraft's operational life. Soviet test pilots like Viktor Belenko clearly understood by the mid-1970s that existing systems couldn't intercept the Blackbird, and their testimony indicates that conclusion was shared among elite fighter units with direct experience attempting intercepts. But broader Soviet military and political leadership may not have fully accepted this assessment, as evidenced by continued missile development programs, massive expenditure on air defense systems, and thousands of missiles fired at aircraft they theoretically understood they couldn't hit. The firing itself served multiple purposes beyond actual expectation of a kill. It maintained readiness. It denied the Americans completely free operations, it provided valuable data on missile performance at extreme altitudes, and it demonstrated resolve even in the face of technical inferiority. For American crews, the psychological advantage of flying an aircraft that enemy forces couldn't reach provided confidence that translated directly into mission effectiveness. Pilots could focus on navigation, sensor operation, and mission objectives rather than constant threat evasion. They could fly planned routes with precision timing, confident that maintaining altitude and speed provided protection from ground threats. They understood that their aircraft had performance margins beyond what they routinely demonstrated, and they knew that immediate acceleration would defeat any intercept attempt that came close to succeeding. This combination of technical superiority and operational confidence created a reconnaissance capability that shaped intelligence collection throughout the Cold War and influenced Soviet strategic thinking in ways that extended far beyond individual missions. Kelly Johnson died on December 21, 1990, at age 80, just months after the aircraft that represented his greatest design achievement flew its final operational mission. He had led the Skunk Works through 40 years of classified programs, creating aircraft that consistently exceeded what conventional wisdom said was possible, and establishing design and management principles that influenced aerospace engineering for generations. He received the Collier Trophy in 1963, the Medal of Freedom in 1964, and the Daniel Guggenheim Medal in 1981. He retired in 1975, but remained connected to the aerospace community and continued advocating for the design principles that had made the Skunk Works successful. Small teams, minimal bureaucracy, absolute authority for project leaders, and relentless focus on performance rather than process. The SR-71 stood as the culmination of these principles, an aircraft that succeeded because its designers were empowered to solve problems without organizational interference, and because technical excellence was valued above all other considerations. Soviet air defense personnel who attempted to intercept SR-71 aircraft throughout the Cold War were not failures despite their inability to achieve a kill. They were skilled professionals operating sophisticated equipment against a target that simply exceeded the performance envelope their systems could reach. Major Miyake and his fellow MiG-31 pilots demonstrated exceptional skill in achieving radar lock and positioning their aircraft for theoretical intercept solutions. Soviet missile operators refined their tactics and firing solutions to maximize probability of intercept under extremely unfavorable conditions. The fact that these efforts consistently failed reflected not professional incompetence, but rather the systematic American advantages in materials science, propulsion technology, manufacturing precision, and operational doctrine that created a reconnaissance platform no existing Soviet system could counter. The broader strategic meaning of the SR-71's invulnerability extended beyond intelligence collection to the fundamental competition between American and Soviet systems. The Soviet Union produced excellent theoretical scientists, highly trained engineers, and sophisticated weapons that demonstrated real capability in many contexts. But the systematic challenges of Soviet industrial organization, material constraints, manufacturing quality control, and technological integration meant that even when Soviet designers understood what needed to be built, the implementation consistently fell short of American capabilities. The SR-71 wasn't invulnerable because Soviet engineers didn't understand how to build interceptors or missiles. It was invulnerable because the American industrial system could sustain the precision manufacturing, quality control, exotic materials procurement, and continuous innovation required to maintain performance margins that Soviet industry couldn't match despite understanding exactly what would be required. The aircraft that entered service in January of 1966 and flew its last operational mission in January of 1990 operated for 24 years in the most hostile airspace on Earth without a single loss to enemy action. It flew through thousands of missiles, dozens of fighter intercepts, and continuous radar tracking by the world's most sophisticated air defense system. It gathered intelligence that shaped American policy throughout the Cold War's most dangerous decades. It demonstrated technological superiority so complete that it influenced Soviet strategic calculations and resource allocation across their entire military-industrial complex. The men who flew it understood they were operating a platform that represented the absolute peak of American aerospace capability, and the men who tried to stop them understood they were facing a challenge their systems couldn't overcome. That combination of American confidence and Soviet recognition defined the reconnaissance competition throughout the Cold War and contributed to the ultimate outcome of that competition. When the Soviet system collapsed under the weight of trying to match capabilities, it lacked the industrial foundation to achieve